Here we are again with another piston cylinder assembly problem. Told you we'd see a lot of these. This one, however, we're going to be dealing with a thermodynamic cycle that has three processes. Process 1, 2 is going to be compression with a product of pressure times volume that's equal to a constant. We're going to go from a pressure of 1 bar, a volume of 2 cubic meters, to a volume of 0.2 cubic meters. And the change in internal energy is 100 kilojoules for that process. Process 2-3 is going to be constant volume. We've got P3 equal to P1. And then finally, process 3-1, we've got constant pressure and it's adiabatic. All right, so what we want to do is we're going to ignore the kinetic and potential energy effects. That's good, saves us some time there. And we're going to determine the network of the cycle in kilojoules, and we want to find the heat transfer for process 2-3 in kilojoules. We also want to know if this is a power cycle or a refrigeration cycle. Okay. First, let's look and see if we have any keywords we need to pay attention to. Now, thermodynamic cycle, that's a good one to pay attention to, because remember, that means it starts and ends with the same properties. Okay, so keep that in mind. For process 1, 2, there's not really any keywords. It tells us compression, but we already know that because it gives us the volumes. You can see the volume does decrease. Process 2, 3, nothing really there. Process 3, 1, we have constant pressure and it's adiabatic. Remember, what does adiabatic mean? Means no heat transfer. All right, so no heat transfer there, so that's a good one to know. And also for process 2-3, let's underline constant volume. That's kind of important to pay attention to. All right, so that's basically what we have going for us there. All right, so we know that, we know some of these values. Let's go ahead and draw this on the PV coordinates, just so you can see what a thermodynamic cycle looks like on the coordinates. So there's V, and here's pressure. We're going to put that in bar. Now for state 1, we've got a pressure of 1 and a volume of 2. So here's 2, there's 1 for pressure, here's state 1. Now at state 2, our volume goes down to 0.2, and we've got this relationship of PV equals constant. So we need to find the pressure at state 2. So in order to find that, we have to use this relationship here. So let's just put PV equals C. So that means that P1 V1 has to equal P2 V2, which has to equal C. Now we have both of the values we need for P1 V1. So we can find C because we can just plug in those values. So we're going to have 1 and then 2, which obviously equals 2. So that is going to equal P2 times V2. So we're going to have P2, that's unknown, and then volume 2 is 0.2. So now when we find our pressure, we get 2 over 0.2. And what does that give us? 10. And units here will be bar. All right, super easy way to find pressure there. So let's put 10 up here, and our volume is going to be 0.2. So put a dot there for state 2. And then we can just draw a line like that. Okay. Now we've gotten to state 2. Now we need to go to state 3. So process 2-3 says we have constant volume and P3 equals P1. Okay. Now P1 was 1. We're at constant volume, so we're just going to put a dot right here for 3. And constant volume on these plots, remember, is always going to be a vertical line. So it's just going to look like that. All right. Now we're almost done. We've got process 3-1. This one's going to be constant pressure, and it's also adiabatic. The adiabatic doesn't matter really on this plot though. So for constant pressure, we just draw a horizontal line and put your arrow going to the right. That's what a thermodynamic cycle is going to look like on the PV coordinates. Okay. Now what we want to do is we want to find the network of the cycle in kilojoules and also the heat transfer for 2,3. So network of the cycle and what that's going to be is it's going to be the summation of the work for each of those processes. So we got work of 1, 2, work of 2, 3, and then work of 3, 1. Okay. So we're going to find each of these works, and then you'll sum them up to get the total. So let's start with this first one. So 1, 2. All right, so here, what we're going to have is work equals the integral of pressure times dV. Now, we already can get an equation for pressure because we have this relationship, right? The PV equals C relationship. So we'll just say P is C over V. Okay. So now, let's go ahead and plug in all of our steps. Let's come over here. So work is going to equal the integral. Our initial volume is 2. We're going to 0.2. Pressure is C over V, and then multiply that by dV. Now remember, C is a constant, so that comes out to the front. So basically you're doing the integral of dV over V. So that is going to give you a work of C, which we're going to say is P1 V1, times the natural log of volume, and then we're going to evaluate at 2 and 0.2. Alright, so that's going to give you P1 V1 times the natural log of 0.2 over 2. Let's go ahead and plug in P1 and V1, check our units, because remember we want kilojoules. P1 is 1 bar, V1 is 2 cubic meters. Now this is bar and then cubic meters. We don't want that. We want to get rid of bar. So that's going to be the conversion 10 to the 5th Newton meter or Newton per meter squared over bar. And then we want to go to kilojoules. So 1 kilojoule per 10 to the 3rd Newton meters. And then we multiply that by natural log of 0.2 over 2. Units there cancel out. So now if you look at your units, everything is going to cancel out, just like you hoped. You're left with kilojoules. So that's going to give you negative 460.52 kilojoules. So this is the work for process 1, 2. Now let's look at process 2, 3. What are we going to get for that one? Now you should be able to tell that just by looking at this plot. We've got a vertical line here. That means no volume change. So if there's no volume change, no work. So this is going to be 0. And again, that's because volume is constant. So this will be another term we need. Now, last one is going to be for process 3, 1. Now this one we do have a volume change. We're going from 0.2 to 2, so we're expanding this point. Now we know P is constant here. The value is 1. So with that we can say work 3, 1 is going to be the integral from 0.2 to 2 of P3 dV. I'll plug in the number in just a second. So when you integrate this, you're going to get pressure times volume. Limits are 0.2 and 2. So P here is 1 bar. Let's go down here. So our work, when we plug everything in, we have 1 bar from P3, and then plug in these volumes. So you get 2 cubic meters minus 0.2 cubic meters. And again, you got to do those conversions. So that's the 10 to the 5th Newton per square meter over 1 bar. Multiply that by 1 kilojoule per 10 to the 3rd Newton meters. Right. So this will make your units all work out to kilojoules. Once you do the calculations, you get 180 kilojoules. So now we know we can find the work for the cycle. So work for the cycle, once we just add these up, we're going to have negative 460.52 kilojoules plus 0 plus 180. Now what do you get when you put all that together? You're going to get negative 280.52 kilojoules. So that is your net work. Oops, I can't see that. There you go. So that's your work. Now, the question asks you, is this a power cycle or a refrigeration cycle? Now, we can tell that just by looking at the sign of the work. Remember, if it's negative, that means work is being done on the system. Now, since work is being done on the system, let's think about a power cycle and a refrigeration cycle. A power cycle, sending work out, right? The arrow was drawn out, so we had an energy transfer by work out of the system. This is saying work's being done on the system. So this is requiring some sort of external energy to come in. Okay? Now that implies a refrigeration cycle, because if you remember back to the picture of the refrigeration cycle, the arrow for work was pointing into the system because you had to have some sort of power supply to make that cycle work. Okay? So this is going to be refrigeration. Okay? So now we know that. Now the next part is to find the heat transfer for process 2-3. Alright, so let's move this up a little bit. I'm going to have to get another piece of paper here. So on this one, what we're trying to do is we want to find Q for process 2-3. Okay, now Q, we're going to have to use the energy balance equation. Right, that's really the only equation we have at this point that we have Q in. So we're going to go back to our energy balance equation. Let's write that out. So you've got your 3 energy terms on the left. They equal Q minus W. Now it told us to ignore these first two. So that's good. We're happy to ignore those. It's less work. And for process 2-3, what was work? We already found it, right? It was 0, so that goes away. So now we've got this, simple looking equation. We know delta U is equal to Q. Now, that'll be good. Now another thing we need to pay attention to is it told us that this was a thermodynamic cycle. Now, if it is a thermodynamic cycle, what does that tell us about the change in total energy? Do you remember? So, a thermodynamic cycle, the change in total energy has to be 0. Now, this summation here is the change in total energy. So what does that tell us about delta U? That tells us that delta U has to be equal to 0. So that's an important detail. We kind of need to know that. So with that being said, let's write out delta U for the whole cycle. All right, so since delta U equals 0 for the cycle, all right, not the process, but the whole cycle, so going from 1 back to 1, then we can write that U2 minus U1 plus U3 minus U2 plus U1 minus U3 equals 0. Now this is going to give us another equation we can use. So that's always helpful anytime we get another equation. So let's move that out of the way. Okay. Now we've got this. Now what we want is this term right here. Okay, so let's go ahead and we're going to solve for this. Okay. And you'll see why we need that in a minute. Remember, we want to find the heat transfer for process 2-3. Okay, so this is the internal energy associated with that. So let's solve for this. So U3 minus U2 is going to be negative the quantity U1 minus U3 minus quantity U2 minus U1. And let's call this equation 2. I just realized I missed a step in here. So let's go back. I hate doing this to you guys. Let's go back and we're going to go back up to here. All right. So we know delta U is equal to Q. Let's come over here. So that means U3 minus U2 has to equal Q23. Let's call that equation 1. All right, I forgot to write that down earlier. I got too excited about the thermodynamic cycle. Totally forgot about this key detail here. All right, so this difference here in internal energies is going to give us Q for 2-3. Let's call that equation 1. This down here is going to be equation 2. Okay. Now, so let's go back down to here. Now, U2 minus U1, this was given to us. All right, so 100 kilojoules was given. So we know that. Now, we need to find this because we know this is our Q. So we've got this, we need to know this. We need U1 minus U3. Now, how are we going to get that? So what do you think? We need to look at process 1-3 again, right? Now we can do the energy balance equation for each of the processes, okay, as well as the total cycle. Now for this one process, let's write out the energy balance equation. So we got our 3 energy terms, and then we're going to have Q13 minus W13. Now we know these two go away. It told us to ignore those, so that's great. Now what else can we do with this equation? Now we've got delta U for 1-3, and then we've got work of 1-3, which we found the work earlier. That's no issue. But what about this Q? We don't know what that Q is, right? Do we know how we could find that? Do we need to find that? Now let's think about our keywords. We said that this process is adiabatic, right? And adiabatic means there is no heat transfer, so this goes to 0. So see how important it is to look for those keywords? If you wouldn't have known that that went to 0, you would be sitting there staring at that for a long time trying to figure out what to do with that. Okay, so always look for those keywords. Now that we've got this equal to 0, this equation got a lot simpler. Now for delta U, we can do U1 minus U3 equals negative work for that process. We already found this value, so we'll have U1 minus U3, and we'll plug in that work value. That gives us negative 180 kilojoules. Now we can take this, plug that back up into equation 2. So let's call this 3. So we'll say 3 into 2, and then that's going to give us U3 minus U2 equals a negative 180 kilojoules minus 100 kilojoules. That gives us 80 kilojoules. Now, we already know from equation 1, the equation I forgot about earlier, that heat transfer is the difference between U3 and U2. So from 1, we're going to say Q23 is equal to 80 kilojoules. So perfect. Now we got our heat transfer. Now let's look at the sign. This is a positive number, so it's greater than 0. That means we've got heat transfer into the system. So we've got energy from heat that's coming into our system. Okay. So perfect. We finished that problem. That's kind of a long problem, but it's a good one. It has a lot of different topics in it, and it makes you really look for those keywords. All right, guys, hope y'all enjoyed that one. That is the end of chapter 2. So I'll see y'all in the next video. Y'all have a great night.